Okay, hi everybody. So today we're going to go ahead and we're going to start working on differential equations and Eulers method. Okay, so two very important topics in the BC world. Okay, so let's just jump right into it. Okay, so time is equal to t is equal to 0. A boiled potato is taken from a pot on a stove and left to cool in the kitchen. The internal temperature of the potato is 91 degrees Celsius at times t is equal to 0. And an internal temperature of a potato is greater than 27 degrees Celsius for all time t greater than 0. The internal temperature of the potato at time t minutes can be modeled by the function h that satisfies this differential equation. So this is the rate at which the temperature is changing with respect to time, where h of t is measured in degrees Celsius and h of 0 is equal to 91. So that's like our initial condition right there. Okay, so A, write an equation that a line tangent to the graph at h at t is equal to 0. So I just got to focus this a little bit better. There we go. At t is equal to 0, use this equation to approximate the internal temperature of the potato at time t is equal to 3. Now, there's a lot to absorb there, but I think the key to doing this is the equation of a line tangent. Okay. You know this because we go over this all the time. What are the two things you need to know in order to come up with the equation of a tangent line? You need to know a point and you need to know a slope. So I need to come up, so I have some sort of a curve h, okay? Whatever h looks like, I don't know. But what I'm going to do is I'm going to take the derivative at some point, and that point's going to be 3. And then I'm going to create the equation I'm going to take the derivative at t is equal to 0. So I'm going to figure out the point is there. So I need to figure out the point. And the point is going to be h of 0. Which, hey, look, I know is 91. Okay? Furthermore, I need to figure out what the slope is. And the slope is going to be h prime of 0. Well, h prime is this thing up here. So this is equal to negative 1/4 times. Now, this is tricky. I'm plugging in 0, but 0 is for t. That's your parameter. T is your parameter. So when you plug it in to this equation, that's like finding h of 0. Okay, so I'm going to go write this out, h of 0, and then minus 27. So this is equal to negative 1/4. But what is h of 0? H of 0 is 91. So I have 91 minus 27. And so this is negative 1/4 times what, 64? So this turns out to give you negative 16. Now, what did I find? That is h prime of 0, so that's the slope. I also know what the point is. It's 0, 91. So my approximation, so I'm going to have h minus 91 is going to be equal to the slope, which is negative 16 times x. But my independent variable here is t, so time. So I have t minus the value there, which is 0. Okay, so once again, here's the point. The point is 0, 91. Okay, that was given. I also know that this is the slope, okay, based off of the derivative. So just plug it in and have this equation. Now what do I want to do? I want to figure out what the value of h is when t is equal to 3, so you plug it in. So if h is equal to negative 16 times 3, the 0 goes away, and then I'm adding 91 to the other side. Okay, so you have negative 48 plus 91, which is going to be equal to 43. Okay, so 43 degrees. Okay, and then to go back, let's go back and make sure that we're answering the question correctly. Does it state, explain, or use correct units? It doesn't do any of that, so we can just leave our answer as is. Okay, on to the next. Okay, so use the second derivative. Now, I don't know what the second derivative is, so I have to go up here and I have to calculate it. To determine whether your answer to part A is an underestimate and overestimate of the internal temperature of the potato at time is equal to 3. So let's first take what the derivative is up here and let's calculate what the second derivative is. So I'm going to write out more than what I really need to, but I want to make sure you guys understand because there's a pretty tricky thing that happens here. and a very common mistake. Now, I'm at the first derivative and I want to get to the second derivative. So what I do is I take the derivative of both sides with respect to t. I'll put that negative there. So I'm going to go dt like this. So this right here, well, that is just the second derivative of h with respect to t, which is what I was trying to find, is equal to, now I'm going to distribute this first. Before I take the derivative, I want to distribute this. So I have negative 1/4 h plus 27 all over 4. Okay, just distributing it there and there. Okay, so now let's go through and take the derivative. So I have the second derivative is equal to. So what is the derivative of negative 1/4 h? You might be very tempted to just say h. But here's the thing, is we are taking the derivative of h with respect to t. Those variables don't line up. So what is it? Yes, the derivative of h is 1, but by the chain rule, you still need to multiply by the derivative of h, which is dh dt. And the derivative of 27/4 go away. Okay? So that's what the second derivative of h is with respect to t. Now I want to evaluate it at time is equal to 3. So I'm going to go to the second derivative of h all over dt squared is equal to negative 1/4, and this is time t is equal to 3. So negative 1/4 times dh dt at t is equal to 3. Okay, now I don't actually need to come up with an answer for the second derivative here. I don't. It says use it, but use it to determine whether this answer 43 is an overestimate or an underestimate. Now, why would the second derivative tell me that? Okay, if the second derivative was positive, that means the graph of h is concave up. Okay, so concave up, it may look like that, it may look like that, whatever it is, but regardless, no matter where I draw on that tangent line, that estimate's always going to be below the curve. So if the second derivative turned out to be positive and it was concave up, then I know my estimate is going to be an underestimate. On the contrary, if it turns out the second derivative is less than 0, then that means it's concave down, so it looks something like that or like that. And now you know the slope of the tangent line is going to be more than it. So all I need to do is determine what is the sign of the second derivative. Well, that is negative. What about the derivative of h with respect to t? So if I go up here, I need to figure out what this is when I plug in 3. Now here's the problem. To plug in 3, I need to know what h of 3 is, but it's nowhere on there. So how in the world did I do this? Most times when you get to a point on these tests and you get stumped, read carefully in the instructions. All the information is there. Okay, so, and an internal temperature of the potato is greater than 27 for all times t. So regardless of what the time is, it will always be more than 27. So this right here is going to be more than 27. So it doesn't matter what value you plug in, but this will be positive, which in turn will make the derivative negative. So that means this is going to be negative right here. This right here is going to be less than 0. Oops, sorry. This right here is going to be less than 0. And I multiply by something that is also negative. That means it's going to be positive. I know that this is going to be greater than 0. Okay, so what does that mean? The graph of h is concave up. So our estimate is less than the actual value. Okay, because once again we're here. It's concave up, and the approximation is below that. Okay? On to C. Ooh, boy, that was ugly. I don't know why it printed off so badly here. Okay, for t is less than 10, an alternate model for the internal temperature of the potato at time t minutes is the function g that satisfies this differential equation. where g of t is measured in degrees Celsius and g of 0 is equal to 91 again. Okay, so the internal temperature is 91 from the start. Find an expression. So there we are. So I want to know what g of t is equal to. Sorry about that. Ooh. Okay, based upon this model, what is the internal temperature of the potato? So you have this differential equation, dg dt, and that's equal to negative g minus 27 to the 2/3 power. Okay. Now, how do you start off with a differential equation like this and get back g? Separation of variables. Okay. You only know one way how to solve a differentiable function here, or sorry, a differential equation here, and that's separation of variables. We're going to go all the g's to one side of the equation, all the t's to the other side of the equation. Okay, so I'm going to multiply the dt up and divide this down. So I have dg over negative g minus 27 to the 2/3 power is equal to dt. Okay, now that I'm here, I'm going to go ahead and integrate both sides. Okay, the negative is a negative, so I can bring it out front. Okay, so this gives me negative. Now, so I'm going to ignore that, and I'm going to go ahead and write it as g minus 27 to the negative 2/3 power. Okay, and that's going to be equal to the integral of dt. Okay, so integrate it. So how do you integrate it? This is nothing more than just a power function, power rule. So you raise this by a power of 1, so it goes from negative 2/3 to 1/3. So I have negative g minus 27 to the 1/3 power. But by the power rule, you also have to divide through by this number. So this is divided by 1/3. Is equal to t plus some constant. The integral of dt is 2. Okay, so flip and multiply. So I have negative 3 times g minus 27 to the 1/3 power is equal to t plus c. Now, how in the world do I figure out what c is? So you do have this initial condition right here. Okay, when t is equal to 0, g is 91, so go ahead and plug it in. So I have negative 3 times 91 minus 27 to the 1/3 power is equal to 0 plus c. So negative 3 times. Okay, so 91 minus 27, that gives me 64 to the 1/3 power is equal to c. The cube root of 64 is 4. 4 times negative 3 gives me negative 12. So that's what c is. Okay, so going back, plugging it back into this equation, actually go to this equation. I'm going to have negative 3 times g minus 27 to the 1/3 power is equal to t minus 12. Okay, so that's our equation. I don't believe, let's see, based upon this model was the internal temperature at times equal 3. So there you are, all you have to do is go ahead and plug in 3. Okay, so I have negative 3 times g minus 27 to the 1/3 power is equal to, so what am I plugging in? I'm plugging in 3. So 3 minus 12 gives you negative 9. Divide by negative 3, so g minus 27 is equal to 3. This is the 1/3 power. Okay, cube both sides, so I have g minus 27 is equal to 27. So g turns out to be equal to 54 degrees. Okay, so based upon this model, what is the internal temperature of the potato at time is equal to 3? So at t is equal to 3, the temperature of the potato is 54 degrees. Okay, so there we go. Let's see. Okay, onward to number 2. Okay, so consider the differential equation dy dx equal to x squared minus 1/2 y. Find the second derivative. So right away, you know you're going to be taking the derivative both sides with respect to x. That's fine with this. If I'm taking the derivative of x squared with respect to x, it's fine because it matches up. But what about the y? Okay, the y doesn't match up, right? So when I take the derivative of y with respect to x, I need to make sure I have the y prime or dy dx. Okay, so I'm going to go ahead and go here. I have dy dx is equal to x squared minus 1/2 y. And I'm going to take the derivative here of both sides with respect to x. Okay, so the second derivative of y with respect to x is equal to, so the derivative of x squared is 2x minus, now, what is the derivative of 1/2 y? The derivative of 1/2 y is 1/2, but the y and the x don't match up, so it's 1/2 dy dx. Okay? Now, you have to pay close attention here because the directions state find the second derivative of y with respect to x in terms of x and y. Right now, I have the second derivative of y with respect to x, but it's in terms of x and dy dx. So I need to go then and substitute in what else I know. And right here is what I'm going to substitute in. Okay, so go ahead and place it there. So the second derivative of y with respect to x is equal to 2x minus 1/2 times x squared minus 1/2 y. Okay, and that is the answer that you're looking for. Of course, you can distribute, you can do some things, but we'll leave it like that. Okay, so this one's tricky. Let y equals f of x be a particular solution to the given differential equation whose graph passes through the point -2, 8. Does the graph of f of relative min, relative max, or neither at -2, 8? Well, how do you figure this out? If you want to figure out the relative min or max, typically speaking, you want to figure out where dy dx is equal to 0. So I have an equation for dy dx right here. So I want to know where that's going to be equal to 0, okay? But I don't really care anywhere else other than at the point 2, 8. So in other words, let's take -2, 8, let's plug it into this equation and see what I get. So I get dy dx is equal to x squared, but the x is -2, so -2 squared is 4, minus 1/2 times y, which is 8. This is 4 minus 4, which gives you 0. So perfect. We start off on the right foot. We know that the point -2, 8 is going to be a critical value. We just need to determine what happens there. So how do I go forward from there and figure it out? It's all embedded right here. Okay? Because think about what happens. I know that the slope of the tangent line is 0. Okay? I know that the slope of the tangent line is 0. Well, what does that look? Okay? That looks like it could be a relative minimum value. It looks like it could be a relative maximum value. Or it could be this funky thing that looks like this. Okay? So it could be one of those. Okay, so what we need to do is we need to determine what is happening to the second derivative at the point -2, 8. If you plug it in to this equation, it turns out that it's positive. What that means is it means the graph of y or f is concave up, which means you're going to be in this boat until you have a relative minimum value. If you plug in the second derivative and it's negative, that means it's concave down. Okay, and if it's concave down, that means it's going to be relative maximum value. And if you plug in and you get 0, you get something like this as your point of inflection. Okay, so let's take -2, 8 and plug this in the equation. So the second derivative evaluated at of y with respect to x is equal to 2 times the x value. The x value is -2, minus 1/2 times -2 squared, so it's 4, minus 1/2 times y, and y is 8. So this gives you -4. Look, 4 minus 4, so this is going to go 0, so it's just negative. It is negative, okay? This implies that the graph of y is equal to f of x is concave down at -2, 8, which means that there is a relative maximum value at -2, 8. Okay? It's concave down, and the first derivative is equal to 0, so we're right here. Okay? The justified answer. Okay, next. Okay, let y is equal to g of x be a particular solution to the given differential equation given this. What in the heck does that mean? Okay, here's what that means. If it is a solution, that means when you plug it in, it works. So if I took the function g and plugged it into this differential equation, it would work. It would absolutely work. Okay? So when I take the derivative of it, it will give me this. So I need to evaluate this limit. Okay, so you know what to do here. Okay, we've talked about this. The first thing you need to do is you need to break it apart. So limit as x goes to -1 of g of x minus 2 all over the limit as x goes to -1 of 3 times x plus 1 squared. Okay, it's pretty clear to see on the bottom it's going to be equal to 0. Okay, now what happens on the top? Okay, so you're evaluating this, so what you really want to know is what is g of x going to as x goes to -1. We have the information right there. It's equal to 2. Okay, so this is equal to 2 minus 2. So you have 0 over 0, so I have to use L'Hopital's rule. Okay, so I'm going to go through and take the derivative both top and the bottom. So in doing so, and I'm going to kind of skip a step. I'm going to distribute the limits as well. So limit as x goes to -1 of the derivative of this, which is g prime of x, all over 6 times x plus 1. Okay, and now what is the derivative of as x goes to -1 of g of x? Okay. Well, do I know anything about g prime? I do, actually. Okay. It's given from the very beginning. So g is a solution to this equation. That means when you plug it in, it should work. If you plug in g for y, you're going to get g prime. Okay. So what I want to do is I want to evaluate it. What happens when it goes to -1? Okay. So I have I guess I'll write here. So I have dy dx evaluated at -1. Now what's the y value that matches up with -1? It's 2. And that is equal to, by this definition, so 1 minus 1/2 times 2. So this is equal to 1 minus 1, which gives you 0. Okay, so it turns out that that's equal to 0 on the top. And then on the bottom, you can see clearly that that's equal to 0 as well. So once again, we have to use L'Hopital's rule. Okay, so this is equal to limit as x goes to -1 of g double prime of x all over, so the derivative of this would just be 6. Okay, so I need to evaluate the second derivative of g at -1. So lucky for me, I have this equation right here. Okay, so once again, I come over here. I'm going to go the second derivative of y with respect to x, evaluate at the point -1, 2, is equal to, okay, and then we have this equation right here. So 2 times x, I'm going to have 2 times -1 minus 1/2, -1 squared, which is 1, minus 1/2 times 2, so it's 1 like that. This all goes away. So you have 2 times -1, which gives you -2. So this is -2 over 6, so it's equal to 1/3. Okay? Okay, and then d, which we do have to do. Okay, so let y equal to h of x be a particular solution to the given differential equation with h of 0 is equal to 2. Use Euler's method, set x equal to 0. So remember what we do, you have to take steps here. Okay? So what we know is we have coordinates x0, y0, x1, y1, and x2, y2. Now, it might be the case where you have to go further than that, right? But you don't have to in this case. The reason why is because x0, y0 is given by 0, 2. And then I'm only taking 2 steps to get to my answer, which is down here, which is what I'm looking for. Okay, so what I want to do is I want to figure out what h of 1 is. So what is the y value when h turns out to be, or sorry, when this parameter turns out to be 1? Okay, so if I'm taking 2 steps of equal length, that means my step is 0.5, right? Because I'm going to go from 0 to 1 in 2 steps. So this one's going to be 0.5. Okay, now how do you figure out the y value? Okay, if you remember what we do for the y value, you start off with the prior y value, plus you add on the step, which is 0.5. but then times the derivative evaluated at the point 0, 2. Okay, so where's the derivative? Okay, so going back to the derivative all the way over here. So there's the derivative here. So you plug 0, 2 into this equation, you get 0 minus 1/2 times 2, so that's 1. So 0 minus 1 gives you negative 1. Okay, so this would be times negative 1. Okay, and then you evaluate this, and you're going to get 0.5, comma, 2 minus 1/2 gives you 1.5. Okay, and then repeat it again. Okay, so now you start off with the prior y value, which is 1.5, plus you add on the step, so 0.5, and then you have to multiply by the derivative evaluated at the prior location. Well, what is the derivative? What's the prior location? Right there, 0.5, 1.5. So we plug it into this equation right here. So maybe I'll go here. So I have dy dx evaluated at, I don't know, maybe I'll do it as a fraction. So 1/2, comma, 3/2. So this is equal to 1/2 squared. Once again, I'm following this equation right here. Just let me move it up a little bit. Following this equation. Okay, minus 1/2 times y, and y is 3/2. Okay, so this is equal to 1/4 minus 3/4, which is negative 2/4, which is negative 1/2. Okay, so this will go right here. Okay, so this is equal then to 1, comma, I have 1.5 minus, so this is 1/2 times 1/2, which is 1/4, so this is minus 0.25. So this gives you 1, comma, 1.5 minus 0.25 is 1.25. Okay, so what's the approximation for h is equal to 1? H of 1 is approximately equal to 1.25. Okay, and that is a good place to stop for the evening. Okay, take care, we'll see you later. Bye, everybody.